Okay, let us start, and potentially today might be the last lecture of this course. Okay, so there might not be any lecture tomorrow or Monday. Anyways, I said until Monday I am available. So potentially the last. Karan, can you close that door? Yeah. Yeah. Thank you. So over the last few lectures, we have been talking about score-based models and diffusion. I mean, both of those, right? And we talked about at least two perspectives of diffusion. One is coming from the score-based model, the other is coming from denoising perspective. Today we will look into the same thing but from a third lens and see if that can give us something new. And yeah, so that's all we will do, and then if time permits I might recap the whole thing that we have done in this course. What are the things that I'm not covering that I wanted to cover, to be very honest? One is obviously GPT. So that part I'm leaving out because covering transformer will take 5-6 lectures, so I don't have that. The other thing that I wanted to cover is I wanted to take one lecture on conditioning, that because all of these generations we are doing is kind of unconditional generation. Like you have images of dogs and cats, we are learning the distribution, we are generating data, and the data coming out is of dogs and cats, right? But can we condition on, let's say, cat, so that the data the samples generated are only of cats? That is known as conditioning. That I wanted to cover, but I'm not covering. But to be very honest, it will not take more than one lecture. Conditioning for all the generative models are more or less the same. One additional things comes into picture, and then your loss function is also function of that thing. More or less, that is how it works. So let us see. Depending on if I have availability tomorrow, because tomorrow is also a class, right? I might take half an hour kind of lecture to talk about just conditioning. But to be very honest, even if I don't cover that, I'm not very unhappy, because I think all of you, it will take you not more than 1 hour to learn that. If you know unconditional generation, conditional generation is 1 hour of going through different ways of conditioning. That's all. So that's why I'm not that worried about that. Yeah, GPT is something that I really wanted to cover, because that will give you some perspective on how some of this large language model works. But that then clearly I don't have time for that, right? So, but that I'm planning to cover next semester, not for those who are in your final year, but in general. I'm planning to cover the next semester, because next semester I'm teaching deep learning transformer anyways will be covered. So that plus 2 will give me GPT. This semester I covered autoregressive, so 2 plus 6 and 6 plus 2, that business. So, okay, so 6 plus 2 is easier. So in that sense, okay. Okay, so with that background, let us start. So we talked about diffusion from two perspective, right? Uh, so we discussed diffusion from two perspective. What are these two perspective? One was based on score, right? And the other one was based on denoising. In the score based, what did we do? Do you remember? We defined something known as score and used the score to denoise. So it was also denoising, but that time the denoising was based on score, right? So in score based model, if I write down the fundamental equation was a SDE, right? So the fundamental equation was d of xt is equal to sigma t d of wt, and this is my forward process or the noising process, right? This is my forward or noising. What was the reverse? Can you remind me? D of xt is equal to what? Did it last week, right? Last Tuesday. What is d of xt? Minus sigma square t, which is a score, dt plus how whatever it is the same. W becomes W tilde, which is a denoising, I mean the reverse noise, which is same as the forward noise. But so this was equal to minus sigma square t gradient of x log of p of xt dt plus sigma t dw t, right? This was the thing, and this is basically time reversed SD. I said the forward process can be reversed. So this is the time reversed SD, right? Time reversed SD, and we will come back to this in today's lecture in some time. Okay, we will need this in today's lecture. That another perspective that we will be talking about in some time. Okay, this was code. The other one was denoising one, the diffusion one, DDPM basically. So in DDPM, what do you do? Remind me. In DDPM, what do you do? You add noise. How do you add noise? So P of xt given xt minus 1 was equal to Gaussian xt, and then tell me what was there? Square root of 1 minus beta t xt minus 1, right? Comma beta ti, right? 1 minus beta t x t minus 1 comma beta t I, right? This is how you add noise. We discussed this. You start from the image and add, keep on adding noise. And why is there a square root of beta? What is the role of that scaling thing? To ensure that at the end of this noising process, you will get a zero mean unit variance, right? Assuming you take some good, I mean, correct beta, which will be what, 0.95 or something I talked about, right? Remember that? So this was the noising process. What is the denoising process? How do you denoise? Remind me. Denoising Q, because this is not exact, this is intractable, right? Q of x t minus 1 given x t is equal to Gaussian x t minus 1 mu theta x t comma t, and then sigma t square, something like that, I sigma t minus 1 t, whatever you write. Yeah, that's something like this, right? Why is it a Gaussian? Is it always a Gaussian? When the step size is very small, then you can Gaussian becomes a reasonable approximation, right? Otherwise, the reverse, I mean, you cannot prove that it is Gaussian. It's a reasonable approximation when the reverse is you're taking too many steps, or the step size is very small, right? So in that case, this becomes Gaussian. And again, because of the same reason, you do not need to learn the variance parameter. That can be constant. Mu is what you will be working with. Mu is to be learned. And how do you learn this? Loss function? Elbow, right? In the last case, the loss function was score based, denoising score based, right? These are things we have discussed, right? So we will come back to this. And by the way, one more thing we discussed. These two perspectives, they are essentially the same. We did not prove it, but I told you that if you represent this mu as xt minus some factor of epsilon and substitute it here, you can show that it will give you the exact score matching loss. So if you represent this mu as mu theta of xt, right, is equal to xt minus some factor times epsilon theta of xt comma t. If you write it in that form, where epsilon is like the one that will denoise, right? If you write it in that form and then substitute into the elbow loss, do some mathematics, you will get the exact score matching loss. Okay? I told you to derive it, I did not derive it. But even after that, sample generation, the samples will not be the same. Why the samples will not be same? Why the samples will not be same? Using score based and denoising? Because when you write down the sampling step, how do you sample in denoising? No, in sampling, in denoising, how do you sample? You sample from this distribution, right? You sample a Gaussian, condition on that Gaussian, sample from this one, condition on that, a chain, right? And that one is exactly, not exactly, similar to the Langevin. The only difference is, no, Langevin do not have a predictor. Predictor is there in score based. But with Langevin, what is the difference? The factors were different. In Langevin, what is the step? Remind me. Xt plus 1 is equal to xt plus eta, then score plus square root of 2 eta, epsilon coming from Gaussian. This is the Langevin step. So there is a eta, there is a square root of 2 eta. When you do this thing using this thing, the other terms will remain same. There will be a score, there will be a Gaussian noise, there will be xt. What will change is that eta factors, they will change. Instead of eta, you will get some factor of beta and alpha, right? And again, same thing for the square root of 2 eta. So as a result, those steps changes. So the direction in which you move remains the same. How much you are moving, that changes. Exploration you are doing using Gaussian remains the same. How much you are exploring changes. And because of that, the samples that you will get will be different. Right? So I'll write it down. So Langevin is basically xt plus 1 is equal to xt plus eta score theta xt comma 1 t plus square root of 2 eta epsilon, where epsilon is from some Gaussian. Something like this, right? Now, as I was saying, these two factors will change. These two factors will changes when you use denoising versus, let's say, score matching combined with Langevin. Okay. Because these two factors changes, what are these two factors deciding? How much you will move. Those are the step length. I think most of you have done optimization course, so those are the step length. What happens when step length reduces or increases? You take a smaller step or a larger step. But that will influence your ultimate optima point, the local minima that you will reach in case of maximization problem. In this case, it will because of this you will reach different samples.
But where do we use this thing? Like we directly from the denoise itself we are sampling. So why do we require this?
You forgot. I told you that you are sampling from denoising. That thing you write in expanded form, you will get this kind of expression. Because mu will take the form of score, some form of score. So from there, when it's Gaussian, right? Write down the expression of Gaussian. You will get this one. Okay. Because of, okay, even with this, what are you sampling from? Can you tell me? Even with this form, what are you sampling from? How are you sampling? Xt is equal to xt minus 1, right? That is, sorry, I'm wrong. Xt minus 1 is equal to mu theta of xt plus sigma t square I times z. That's what you get, right? Now that mu you can write in terms of xt minus 1 minus that thing. So that will give you this form. Okay. Because sampling from Gaussian means what? I mean, let me write that also. So this one, when you sample, what does it mean? It means that xt minus 1 is equal to mu theta xt comma t plus sigma t square I times z. That's what it is, right? Now, this thing you are writing in form of xt minus 1 minus some factor times s theta or epsilon theta, right? Something like that, plus this term remains as it is. Okay, now you see that you can see the similarity now. Okay, so that's what you are doing. You just need two lines of writing these things down and you will get it. Okay, it is not difficult. Anyways, this was all in the last lecture. Let us start today's lecture. Right. So now, let us start from the beginning. Okay, these things, whatever I've discussed or recap, we'll come back to that. But let's start from the beginning. In denoising, in diffusion, in score based, what are we essentially doing? Hmm? Louder. Solving? Solving SD. What does solving SD means? You have to be more fundamental. Solving SD is the technique. But fundamentally, why are you solving SD? What are you doing? What is happening when you are solving SD? That you are doing in all generative models. In these models, what special you are doing?
The evolution of the samples along the time steps.
Not evaluation of samples. Here you are evolution of the distribution. You have multiple distributions. You are trying to go from one distribution to another. You cannot go directly. So what you are doing, you are coming up with a mechanism that allows the sample to go from one distribution to another through a number of steps. Because the first sample that you are drawing during sampling is from Gaussian. Through n number of steps, that n can be 1,000, 1 million, whatever, right? You are reaching a sample which is from the data distribution that you have learned. And in between, if you leave out the first and the last step, everything else corresponds to a different distribution. So what you are essentially doing is that you are navigating multiple distributions from Gaussian to reach the data distribution from the Gaussian. That is essentially what you are doing, and that was shown. I mean, it was not that I did not say it explicitly, but that was shown through that diagram where there was a mixture of Gaussian and we keep on adding noise. So what was happening? We were getting different distribution in the middle strips, right? You remember the diagram, right? There was a mixture of Gaussian and then you keep on adding noise. At the end, you end up with a Gaussian, like this diagram. So the diagram was this one, right? And then you add a little bit of noise, it will become, add a little bit more noise, it will become, and you keep on adding noise, at the end you will get, right? This is the diagram we saw earlier. And you can see that at each step the distribution is different, right? So, and while noising forward process, you are going from left to right, while denoising, while sampling, you are going from right to left. And we called it as, remember, we called it as P of x0, P of x1, P of xt. Correct? Right? So, what we were doing, be it score based model, be it denoising, both the same thing, both are diffusion. What we were doing was, we were navigating through multiple distributions using SD, as you correctly pointed out, to reach the data distribution starting from the noise distribution. Everyone agrees? Right? So, we were navigating different distributions, right? And what was helping us navigate this different distribution? Who was guiding us? What was guiding us to navigate between these distributions? There was one thing that was guiding us throughout. What was guiding us? The score was guiding us. The score was guiding us because it knew we were computing score corresponding to each of these distributions. Score is a function of t and xt, which means the score was not for a given distribution, it was for all the distributions. So it is the score that was guiding us to navigate between these distributions. So remember the score? It is xt comma t. That was a single score for all of this distribution. It was not a score for one distribution. Correct? So what was helping us? Score. And we were navigating via score. Okay. So fundamentally, this is what we were doing. We were navigating different distribution in a random walk kind of manner, in a random fashion, right? Stochastic. But there was a guiding principle, and that guiding principle was the score. We were doing random things, random steps. Epsilon was not random. But the score was kind of pointing that no, you should go in this direction. Right? So it was like random navigation. Right? That is what we were doing. Now, in all of this thing, the distribution, and distribution can be thought of as collection of samples also, was evolving. Distribution was evolving in all of those things, right? But when a distribution evolves, the integration of the distribution should be equal to 1, and all those quantities holds, right? So there is some conservation that is there, I mean, right? So can we use those conservation and concepts from mechanics to do the same task? So when something is conserved, what is the law do you use? Continuation, right? That transport, right? And so can we use those kind of principles? Is what we will try to look into today. Can you use some of the things that we study in solid mechanics, fluid mechanics, mechanics in general, to solve the same problem? Because it is like one of the particle is getting transported from right to left, right? So the continuity equation should hold. Total inflow should be equal to total outflow. I mean, nothing can be created or destroyed. So whatever is coming in, based on that, what is going out, that should match, and if it is only coming in, the density should increase, and so on and so forth, right? So that should hold. So now, so there are two concepts in mechanics, or two reference frame, I will say, frame of reference. One is the Euler, or two description. One is the Eulerian description, the other one is the Lagrangian description, right? All of you know about Lagrangian and Euler. Is there anyone who does not know about Eulerian and Lagrangian? You don't know. Anyone else? So Eulerian and Lagrangian is how, if something is happening, how you are observing it. Okay. The way you can think of it is that, suppose there is a river and there is a boat that is going on the river. Now you can observe the phenomena that is happening from two point of view. One is you are sitting on the bank, you are observing a section of the river, only that section you can observe. You see the boat coming into that section and exiting that section. This is one point of view you can think of, right? That is the Eulerian description, where you are not, you are observing a volume and you are seeing whatever is happening in that volume. Okay. The second one is Lagrangian. That is simpler. You are sitting on the boat and observing. So if you are sitting on the boat and observing, you are basically tracking the particle. You are not observing any volume or section, you are tracking the particle. This is the Lagrangian. Okay. So there is the Eulerian description and there is the Lagrangian description. Fluids, people solve mostly using Eulerian. Solids, people solve mostly using Lagrangian. But there are, I mean, they can be interchanged, but things in a standard manner are described in that way. Okay. So that is the Eulerian and Lagrangian. Others, I guess, already knew this from solid mechanics and strength of material course. But yeah, so that is the Eulerian and Lagrangian. Okay. So let us take the Lagrangian description, right? First of all. Lagrangian description. In Lagrangian description, what are you observing? A particle, right? And the particle is changing position with time. So then, in the Lagrangian description, can I not write dxt by dt is equal to Vt? I mean, you don't even need to listen to Lagrangian or anything. Gradient of position is equal to velocity, you know, right? But this is the Lagrangian description because you are observing a particle and seeing it move, right? What is the Eulerian? Eulerian gives us the continuity equation. So del, in Eulerian it becomes del because there is space and time. In Lagrangian, you were sitting on it, so you were only observing the particle, right? So that was a total derivative, that's why. Del rho of t del t plus grad of rho t v is equal to 0. This is the continuity equation, right? I mean, this is something that is often used in fluid mechanics, right? Which means that if the inflow is more than the outflow, then the density should increase. If the inflow is less than the outflow, then the density should reduce. That's all that is it is saying. And that's common sense, right? Think of a gas, right? If you increase the inflow and the outflow is less than that, then the density increases, right? So in that sense, okay. In this case, what is rho? PDF, probability density. Okay, this is not density of some gas or fluids. This is density of, because these particles are representing the PDF. So this density is of the PDF. I mean, so it's the PDF. This is not of the PDF. This is the PDF, right? Okay. So which means those part X were the particles or samples from this PDF. Clear? What is happening? So xt basically is a sample drawn from rho of t. Okay. Rho of t is rho of xt basically. or P of xt. Any question?
What does V
V, yeah, it should be Vt. What was the V in the left hand side? Same thing. Velocity of the particle.
How does the velocity term mean here?
It will mean, right? I mean, you will integral, right? Or the volume. It will be the integral. So in that sense. Okay. And that's why, so basically this is at a point but you are taking a derivative and then to solve it you will integrate over the total volume, so you will get it. So okay, you will, so in that sense.
So in distribution, like in distribution, if we take integrate, then it will give the CDF. So it's kind of like a CDF. Is it something?
No, distribution only gives you CDF when you integrate with respect to x.
Yes.
Here you are integrating with respect to t, not x. So this will give you how the distribution is changing with time, right? Which is exactly is this one. How the distribution is, so integration with respect to what? If you integrate with respect to input variable and go from minus infinite to infinite, you will get 1. Or minus infinite to something, you will get the CDF. But here integrating with respect to time, right? So that means this is the evaluation of the PDF. How the PDF is evolving over time. We will not use the right one. Right one is only for your understanding. Left one is what we will use. Okay. So as long as you understand the left one, which is the easiest one to understand, you can. Okay. Everyone follows this too, because everything will follow from here. Okay. So now, remind me, I'll ask again, what is xt? Sample. And what does xt equal to 0 and xt equal to 1 mean? At time, right? Which means evaluation of the particle. Which means, as if I take the same notation, right? As x capital T is what? T equal to capital T in this case. So that's a sample from the Gaussian distribution. What does xt equal to 0 means? A sample from the data distribution. And then there will be intermediate steps. Correct? Now in this case we will reverse. T equal to 0 will mean Gaussian. T equal to T will mean data. We will reverse the notation here. But you understand what will happen. And we will reverse because we don't need the noising process now. So if the noising process is not needed, so why will I name it like that? So in the denoising, first noising came, then denoising came. So we use that notation. In this case, it starts directly from noise. So this step is gone. So we will reverse and say 0 to in that sense. Okay. Okay. So now, what is unknown here in the left-hand expression? V is unknown. So if I can somehow find V for a given target distribution or evaluation of distribution, I should be able to solve this equation and draw samples in a deterministic manner. Now there is no uncertainty now. This is a ODE. So it will be a deterministic way, and in a deterministic manner we should be able to reach the final t equal to 1 is what we use, which will be equal to the sample from the data, not data distribution, right? But all of this we can only do if Vt is known. Unfortunately, Vt is unknown, right? So we need to model V somehow. If we model V, we will model V using neural network that you know already. So if we can model V using neural network or something like that, then we can use that neural network to do this thing. So I'll repeat once more. In diffusion, in score matching, whatever we were doing, it was evolution of the distributions, the PDFs, right? At least during the denoising process, also during the noising process. The direction was reversed, but it was evolution. We were traversing through different PDFs to reach the data PDF, right? So if it is traversing and traveling like that, can we not write it in form of an equation that we know from mechanics when particles travel? which is in the Lagrangian description is the one on the left hand side, in the Eulerian description is the one on the right hand side. The right one is the continuity equation, right? Now we will work with the left hand one, that is simpler. And if we work with the left hand one, let's say, and if we know V, we should be able to now draw a sample from Gaussian, and using this V we should be able to solve this time integration, and that will give me a deterministic one-to-one mapping between the sample and the noise and the data sample, right? But all of this we can only do if V is known, right? But V is unknown. Clear?
So,
Any question? Yeah.
but here we are just, it's like we are not, in the previous case, we are taking kind of like a Brownian motion, random walk is going how it is, we don't know. So that approximate the whole behavior much better compared to this direct approach.
Yes and no. And I'll tell why. Okay. First of all, I mean, if I have to compare the two, let's say, you can imagine this is like you have a map and you are following the map to go from one place to another. Okay, so you have a very deterministic kind of map. You know, if I follow this path, I will reach here and there and all of those things. Your goal is to explore the map. That does not change, but you have been given a map now. In the other case, it is like you do not have a map, but you have some direction. Okay, there are trees. I can see footsteps, so I should go in this direction. And then the footstep vanish. Okay, let me explore three directions, and okay, this again the footstep appeared. I will do that, and that is how you are exploring. The other way is that you can think of it like a conveyor belt, where there is a direction you are going from one place to another, whereas the other one is like a boat on a river, where based on the flow of the river, it can be slightly here and there. So now, which one is better, and what is your goal? It depends on that. If you have infinite compute, maybe the SDE one is better. You do not have infinite compute, so you will want to reach from xt to x naught as quickly as possible in a deterministic sense, if possible. You will don't want that it should go here and here, get diverted and reach there. In that sense, it will be better.
So in here, our objective will be to find the shortest path to reach there.
Ideally, we will not be able to find that, but ideally.
Ideally, that.
Yes.
So what about the quality of samples in terms of diversity?
Correct. Quality of samples depends on multiple things. Remember, even in denoising, we assume that it's a Gaussian. So quality of samples depends on that. In this case, if you know the exact V, you will get the exact samples. And that comes from a theorem known as optimal transport theorem. Optimal transport is a theorem that says that you can transport between any two distributions in a deterministic manner. Okay. So ideally, the optimal path is the optimal transport. In this case, you will not find the optimal transport, but you will be approaching or trying to learn the optimal transport.
And so, as you said, like the diversity will reduce in this game?
Not necessarily.
Not necessarily.
In fact, no. The answer is no. Because optimal transport is a valid theorem that holds for any distribution. So as long as you have enough diverse sample in Gaussian, and there is enough, there is a one-to-one mapping, right? So each distinct sample in X will give you a distinct sample in the target.
So now diversity will totally depend on the.
It will depend how diverse your sampling is, right? And obviously how good is your V. Learning V is the challenge, obviously, but if you can learn V, then. Any other question? Okay, so let me write it down then. So the question is, can we use Vt to sample X from P of D? This is the question that someone asked, hopefully, right? I did not ask this. I'm asking this now. And obviously the answer is yes, but someone asked this question, right? That's why flow matching came. Okay. And the idea is yes, we can, if we can learn V. And our answer is yes. if we can learn V. Okay, or if we know V. V is what? A velocity field. So from the scored field, we are going to velocity field. Both are vector field. Scored was also vector field, right? So the question naturally is how to learn V. Because you do not have anything to train V on. What will you train V on? You don't have anything. Do you know the relation between V and let's say a given distribution? You do not know that. So how to learn V, right? So that's the question. To learn V. The first challenge is we do not have any supervision that can allow us to learn V. Okay, which means we need, when there is no supervision, no data, what we do is that we make some assumptions, we try to model things, and from that model we try to learn. Okay, and whenever we do model, whenever we model something, the models are always based on some assumptions and approximations. Okay, there is a very popular saying, statement, quote: all models are wrong, some models are useful. Okay, so that's a very popular quote. Okay, so we have nothing to that can supervise us, right? So how to model V? So this is what we do. See, V. So first of all, t equal to 0. This represents, what does it represent? T equal to 0, what does it represent? Noise, opposite. So t equal to this 0, we have, okay, maybe I should write something else. Let's see. We have x0 from p of 0, and this is noise. Okay, p of 0, rho of 0. I think rho is the correct terminology. Okay. At t equal to 1, and here we will only go up to 1, we have x1, which is from p1, which is what? Data distribution. Okay. And what you assume is that it follows a linear path. Okay. So the assumption is as follows. This is t equal to 0. This is your x0. This is t equal to 1. This is x1. I want to know what will be the value at t. What will be x at t? Okay. So if I make a linear assumption, then what will be x at t? What will be x t equal to? Simple, draw like this, right? So it will be first of all x naught plus x1 minus x naught by 1 multiplied by t. That's what you will get, right? Which will obviously be equal to 1 minus t times t. That's what you will get. This is equal to what? x1 times t, t times x1 plus 1 minus t times x naught, right? So this allows you to find xt. Xt is what? Position of a particle at time t. With this assumption, I can find it out, right? Now, if I know xt, what is dxt by dt? That is my vt. So with this, so this implies dxt dt is equal to what? x1 minus x0. Right? And with this, you have a recipe to find out Vt. This is a Vt. So this is also equal to Vt. That's also.
The difference between the PDF will help us with
This is not PDF, this is samples. Okay. Which means I can now use this Vt as my target and train a neural network which should learn this Vt. Which means I can now have a neural network which is supposed to give me velocity, and I have a target for that, which is this Vt. So whatever the neural network output is, that should be equal to this Vt. Right?
So for given any defined sample, we will have the value of V, and that way for all the data sets we will have. So for V also we will have the kind of distribution.
Obviously. Obviously. Because V is a neural network, right? If you change xt, V will generate. Now, what that distribution is, I don't care, no one cares. But can you feed a distribution? You can go ahead and feed a distribution. Who is stopping you? Right? It will not be constant. And everything has a distribution. What does not have a distribution? Everything has a distribution, right? Is the distribution important? No, it's not. At least not in the context of this. Okay. That is velocity of a particle, right? So with this, how do you train? So we use Vt as target to train V theta xt comma t. What is V theta xt comma t? The velocity field that is to be predicted by neural network. By the way, why do you need this thing? You have already Vt. Why is V theta needed? I can find out Vt simply by sampling and doing this thing. Why do I need Vt? V theta? Hmm? Yes, so if we have let's say, a million samples, I don't need it. It's a trivial question. Don't get confused because I asked it. Because during sampling, we will not have x1. During sampling, we will not have x1. That's why you need it. It's a trivial question. Okay, but many people gets confused that if I can find x1 minus x0 and that's my Vt, why do I need to train a neural network for such a simple quantity? You need it because you don't have x1 for your
Next time step.
when you want to not time step. X1 is the actual sample, but during generation you don't want to generate the same samples you have. You want to generate new samples. So x1 is not known to you during sampling. Okay, so let me write down the algorithm, and that will make sense hopefully. So algorithm. Your input is your data, which is x of I equal to 1 to n, right? You have data as input. You also might have, you might provide as input the batch size and all of those things, but I'm not writing that. Okay. So here is what you will do. Sample x naught from Gaussian 0 comma I, which is basically noise, and you will sample, I mean, how many samples will you draw? Equal to your batch size. Okay. You will, because if your batch size is 16, you should draw 16 samples, because you will work in batches, you cannot work on the total data, right? And then step 2 is sample x1 from P of D. Again, this is also equal to the number of batches, batch size. Okay. Okay. Third, you will again sample. What will you sample? Time in uniform from 0 to 1. Again equal to the number of batch or batch size. Now not number of batch size is the correct term. I should write batch size. Batch size is what I have written here. Okay. So you have 3 things now. Using the 3 things, what can you find out? You can find out xt, and that is your 4th step. Xt you are going to sample, not sample, xt you are going to compute, and that is equal to what? T times x1 plus 1 minus t times x naught. So xt also you will have equal to number of batches, I mean not batches, batch size. Okay. And also you will calculate, what is the other thing you will calculate? Vt, which is equal to x naught. Okay. Finally you will maximize your or minimize your loss. So the last step is theta star is equal to arg mean of theta. Let's say batch size is equal to m. So 1 by m summation let's see, you have Vti minus S, not S, V minus V theta x t I square. Right? And this will, and you will repeat it for all batches, do all the gradients and all of those things, that will give you your theta, which means you will know your V theta. Clear? Any question? How will you sample? Sampling, you can use any numerical technique that you know, it's fine. The easiest one is Euler. You can use RK4, you can use any time integration scheme of your choice. Right? Okay. What is the bottleneck of this method? The assumption that it's linear. And because we are assuming it to be linear, it's not the optimal path. And because it's not the optimal path, so the path is suboptimal, right? So one way of improving it is that you use some optimal transport theorem to come up with the best kind of path that you should take. Now, yeah, that is, I mean, how to model it is an open problem, I will say. People are trying to model it using different things, and that can many more things can be tried. Optimal transport by theory is the best way, but optimal transport using that to find out this thing is not easy. So this is a very easy assumption, very easy to implement, nothing to derive, one line. So if you make it complex, the error will reduce, but the derivation part and implementation might get little tricky.
So you are saying that here we have taken this linear.
Correct. That's an assumption. That's an assumption. That need not be. That need not be. That is obviously definitely not the optimal path, because this is ultimately a path from going from x0 to xt. Is that the optimal path, the shortest distance? No. Shortest distance is the optimal transport path. Yeah.
Can you explain me this? Why we require this 60 value?
What will go inside the VT?
But that is okay, sir. But in the VT, we only require the last image and only for the
Correct. Correct.
the data set we have.
Correct.
And for those things we require. But XT may be the middle step.
What is inside V theta? What is the input to the neural network?
Why it is?
Why it is?
Why it is not XT? X not. Why it is?
What is it? Right? Tell me a generalized ordinary differential equation. What is the form of a generalized ordinary differential equation? dy by dt is equal to f of y. So in this case, that f of y is v. Dx by dt is equal to v of v, right? V is function of what? X. Generic x. So now when you do time integration, will you go from 0 to 1 in one step?
Okay, so here V theta will because VT will have the one step full answer, na, sir?
V is constant. Velocity constant does not mean position is constant. Velocity constant does not mean position is constant. For example, I'll give you an example. dy by dt is equal to, in your case, v of y. This is what you have. Now this v of y can be found out as y naught minus y1 minus y naught or whatever, right? But this is ultimately a function of y, right? Now this is that one. Now when you do it, solve it using Euler, what will you do? Will you say that y1 or y capital T, let's say, is equal to y0 plus total time capital T times v of y? Not. Is that what you will do? Will that be a correct result? No, right? So this is wrong. You take small steps. So what do you do? Yt plus 1 is equal to yt plus delta t v of yt. This will keep on changing, which means v is function of, v should be learned for different y values. V should not be learned only for one y value. If you are learning v for only one y value, then that v will not generalize in your intermediate steps.
Here I can understand. Sir, in the neural network, how it will be? I'm not understanding.
This is the neural network. Where is it? This is a neural network. Now done, neural network.
The confusion comes from like the input to the neural network is a sample from a distribution somewhere between t equal to 0 to
Correct.
and the neural network is then transporting it to the desired distribution.
Correct.
So
Because the velocity is constant, no matter from where you start, the velocity does not change. Which means, if I go to this diagram, if you start from here, velocity is the slope. Remember, keep that in mind. If I start from here, 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 wherever I start, the velocity is constant. So it should learn that.
So due to the assumption that velocity is constant, that's why we are not giving time as input.
We also give time. I wrote it wrong. Time should also be, that is wrong. That is a mistake on my side. Okay. Because you want to make it generic, right? More information. So time is also an input. So that too. Time is given as input because that's like an additional information, right? And that allows the model to generalize because you will probably not always work with a linear model. You might come up with your own optimal transport model. In that case, time has to be input, right? But in general, time you do not need. I mean, if I go strictly by mechanics principle, we don't need time. Time is there implicitly as function of, because v is y is function of that. Okay, so what I was saying is very simple. Dx by dt is equal to v of x is valid for any x,
Ah,
right? If it is valid for any x, you should be able to find v for any x.
so that's why it is like we are taking.
And it is constant for any x in this case.
Yeah, so for every time step we calculate that
Correct.
value and taking the average of it.
Yes.
1 by n is the.
You will get same thing only, but yes. Okay. Here the mean square is not over batch. It is over batch, right? It is over batch, not over time. M is not your time. M is your batch. So we are not taking, because for each sample I have only taken one time point.
Ah,
I don't have multiple time for each sample. Each sample I have taken only one, right? Because I have sample t in 0 to 1. So I'll get what? 0.1, 0.9, 0.8, 0.7, 0.675, these things. Each of these corresponds to a time for a given sample. So, and because it is easy to learn, so that will allow it to learn that for each of the sample, this should be V.
so the t we take on that, it will depend that how much it will.
Yes.
It get much better.
Yes. Yeah, the T thing I had to write. Where did I forget here? Comma T.
So would we require multiple inputs if we don't give t implicit?
In this case, probably no. In most cases, theoretically, no. Practically, you don't know. The network might not. Because see, the information of T is already there inside X of T. Right? But, I mean, at least theoretically it is there. Practically, it is not there. Because X naught you are sampling independently. X naught has nothing to do with XT. And then using that X naught and XT, you are coming up with some number, which is a function of T, but how will the neural network know that? The neural network will not know that. So you're cooking up something based on these two terms. So the neural network will not know that. So that's why T is also important.
So it's kind of a condition we are doing.
Kind of, yeah, additional information.
And in the sampling, where do you put this Euler and Kepler? You have.
Let's go back. Here, Vt will become V theta of xt comma t. So you will first, your initial condition will be a sample from a Gaussian noise. And then you do Euler or RK, you will get your sample. So basically it will be like this, right? So after all of this is what you got, right? So let me write the sampling algorithm also. So sampling will be what? You will draw x naught from some Gaussian 0 comma I, and then for t equal to 0 to 1, your x t is equal to x t minus 1 plus delta t v theta y t minus 1 comma t minus 1, something like this. And that will, and once you reach 1, that's your sample.
And this t need not to be the same t the numbering value in the training we use.
No, nothing. This is some uniform interval. This is time integration, and you are only interested in t equal to 1. Other things are not of interest to you. Okay. Clear? This is known as flow matching. Flow. Just now I said at the beginning, right, that if you know flow matching, conditional you can learn on your own. That's what I was saying at the beginning. This is not conditional. There is nothing conditioning here. Okay. This is for flow matching.
So sir, if this is a one-to-one mapping, can we not put any neural network in this
You can.
neural operator type?
You can. Definitely you can. And by the way, those who have done a machine learning course earlier, do you see similarity with some method you know in this case? There is one method with which there is similarity here. I don't expect many of you know, but one or two of you should know. Neural ODE. Neural ODE follows the exact same principle in some other concept, but it somehow is okay. It is neural ODE. If you look into it, it follows the exact same concept, but it is not a generative model. Okay. Training in neural ODE is much more difficult, obviously, but the model is same. Last thing, okay, before we wrap up, does it have any similarity with diffusion? Is there a similarity with diffusion? Is there a one-on-one mapping with diffusion? And so on and so forth, right? So remember at the beginning of today's lecture, the equation I wrote was d of xt is equal to sigma t dwt, and the time reversed equation was minus sigma square t grad of theta log of p of xt dt plus sigma t dw tilde t, right? The second SD is of interest. So in SD there is a concept of Fokker-Planck equation, and using the Fokker-Planck equation is what you know. I wrote it in some sense from where it arrives. Fokker-Planck equation arrives from the right hand equation. If I write in Eulerian description, I will end up with the Fokker-Planck equation. Fokker-Planck equation is what? What is SD? What is SD? What does it tell?
behavior of the
Evaluation of a random process, right? And at each time you get a different PDF, sorry, probability density function, right? Now the probability density function evolves in time. The Fokker-Planck equation tells you how the PDF will evolve in time. The original equation was Fokker-Planck equation, then came the Fokker-Planck-Kolmogorov equation, FPK equation is what we call it, which is the most recent version. Okay. Fokker-Planck-Kolmogorov equation or FPK. FPK equation tells you how a random process, if you discretize in time, how the PDF of the discretized random variable will evolve in time. That is the Fokker-Planck equation. Okay. So this equation that I wrote, where is it? The right hand side, this is like a Fokker-Planck equation, and Fokker-Planck equation comes from this continuity equation only. There is some, if I have to derive something, I have to use this.
if we see in a Eulerian space,
You get the
then we
Fokker-Planck
use
equation.
that behavior.
Right. Okay. So keep that in mind. And now, using the Fokker-Planck equation, you can have an equivalent ODE for this. Equivalent ODE you can get for this one, which will take the following form: dxt dt is equal to minus half sigma square t grad theta log of pxt. Okay. This, and I told it when I talked about SD the first time, I told you that there is an equivalent ODE also. I will come to it later. This is that equation. And you can see that it is very similar. It is like taking the expectation and then a half is extra. Other than that, if you take an expectation, you will exactly get this term. Because with expectation, dw will become 0, so that will vanish. The right hand side will remain. dt you take this side. The half is extra, that is from the derivation. I'm not going to do that. This is the equivalent ODE for the time reversed SD. Okay. So from this equation, what is velocity? The right hand side is the velocity. So velocity field has a direct relation with the score. So this term is score, right? This is your score.
That could be X.
X, yeah. Thank you. And this is your V theta of. So velocity field and score field has a direct correspondence. Okay. So flow based model, some people will say is a special case of diffusion model, whereas there is another group who will say diffusion is a special case of flow based model. You can choose your side. I am in the middle. And I would like to be in the middle. I don't like to pick sides, but we will find both sides. Okay. Those who work on diffusion will say flow based is a special case. Those who work on flow based will say diffusion is a special case.
So, sir, training with this approach and direct flow matching approach will give similar result?
Yeah, both are both give good results, but they will not be similar because it depends how difficult. I mean, learning V theta and S theta, both you are learning, and they will not be same when you learn them. They will not be equivalent also when you learn them.
Yeah, but chances are that this.
If they become equivalent, then it will be same. Assuming you use Euler scheme to sample from flow matching and Euler Madhumama to sample from this one, because there is some sampling error also that will come. So there is a one-on-one correspondence between Euler Madhumama and Euler. So assuming that. Okay.
So there also we have corrector. Similar also we can put it.
You can
here
put
also.
something, but how will you put it? There is no uncertainty here. It's the deterministic path. What corrector? You can use a better, the original corrector predictor you can use.
Yes,
But
so
the original one, not that one.
that deterministic.
Okay, so you can use that, but ultimately they will not be same because learning this to the objective function is different.
And so Euler Madhumama will come whenever you do it for a SG scenario.
Correct. Because this is in S theta.
We can do the Euler and that we can put the corrector.
But corrector will not come. Corrector only comes when each of your point is a random. In this case, you are getting a sample which is not random, it's a deterministic mapping. So there is no stochasticity in each point. It's a deterministic path, right? Map I say.
Signal value, not the.
So you cannot. Okay. So let us summarize, right? Let us first summarize this thing and then summarize the whole course. Okay. So we started this part of the course at least by talking about energy based model. Energy based model has limitations, we said, which is contrastive divergence sampling. We said, can let us use core that will allow us to better, in some sense, right? Better, that will help us in scaling things because you need one gradient less. So we talked about score, but score also needed Hessian and not Jacobian. So we said, okay, let us use denoising score. And then we said that denoising score, there is some balancing act. So let's use multiple level of denoising. And then we said if you're doing multiple level, ideally it should be infinite. So we went to SDE. And that gave us the first diffusion model, which was based on score, which was score based model with SDE. And then from there we go to denoising, where we say, okay, why should we do that? Let us do qxt minus 1 given xt. Qxt minus 1 given xt will also give the same thing. And that's what we did. And then today we said that let us look into another perspective, which is that can there be a velocity field, and we'll do it in a deterministic manner. Lagrangian, Eulerian, whatever you take. We took the Lagrangian one, that's the easier one, that's what everyone takes. And there we now looked at the same thing, but now we are sampling or using the velocity field. So there is very close relation between score based model, diffusion, and flow based model, flow matching, not flow based model. Okay. This can also be related to normalizing flow, but I'm not doing that. But normalizing flow, that invertible mapping that you get here in continuous form in some sense. Okay. I'm not doing that, but yeah. Okay. So this is what we did over the last, I don't know, 1 month. at least 2 weeks, 3 weeks. We did this thing, right? If we took energy based model, it is almost 1 month. Overall in the course is about generative model. We call it generative model. It means it is a model that can generate new samples. It learns the distribution of the data and it use that to generate those new samples. In the course, we talked about initially about autoregressive generative model. Then we talked about latent variable model, which is VAE. By the way, in autoregressive generative model, we talked about NAID, MAID. We did not really talk about it, but those things are there. In the homework, you did it, or practically you did it, right? Also, that fully visible sigmoid FBSBN or something like that, sigmoid, right? FBSBN, right? So all of those things we talked about. In VAE, we went to VAE, did all the derivations, and we saw that the optimal one is when you sample from Z. So X given Z, Z given X. So that's how the encoder came into picture, right? Encoder is not there by default. We saw how it came. We then talked about flow-based model, which is different from flow matching in some sense. Also, there is some similarity. In flow-based model, we generally rely on invertible mapping. We want, and that's how the distribution flows, we said, which is also happening here. And there we talked about different variants using autoregressive invertible, forward, reverse, teacher student. We talked about usual real MVB and all of those things, right? And then we talked about GAN. GAN was something likelihood free. So we said that likelihood sometimes creates problem. Can we do it in likelihood free? There is a neural network that came into picture, which is the generator. I saw discriminator. Discriminator now has a likelihood, but generator does not have a likelihood, and that's how it works. The problem is mode collapse. The problem is unstable training and all of those things. That is what we did until midterm. After midterm, we started with the energy-based model. In energy-based model, we did 2-3 variants, starting with the most basic one, and then Boltzmann, right? RBM, restricted Boltzmann machine, and so on and so forth. We saw the limitations of energy-based model. It does not scale. Hessian is a headache. So we went to score-based model. Score-based model, we did different variants. From there, we went to diffusion directly. There is a direct linkage, and from diffusion, we went to flow. So that is that. Those are the things we have covered in this course. So at least 5-6 different families we have covered. Those are majorly basically all the families that are there in existence we have covered, to be very honest, currently in the generative modeling paradigm. So yeah, what we have not covered, yeah, we have not covered the conditional part. I'll repeat that. So please read about it. And yeah, one example I wanted to cover, which is of GPT. We have covered autoregressive, but GPT as a case study I wanted to do, but that we are not doing now. Okay. So that is more or less what the course is about. So this is the last lecture for this semester. Exam is on 29th. It will be written 2 hours, whatever the time is. Do the derivations properly. There will be many derivations. I have not made the questions yet, but I know myself, so I'll give derivations. Okay, so be ready for that. 2 more things are remaining. One more time we'll meet apart from the majors, which is the project. I will see how many projects are there and whether it will be a presentation or a poster. I'll let you know soon. Okay. Homework is due. I think homework, you pointed out that the Kaggle deadline has to be changed. So I'll tell Sawan to change it. Okay, Sawan is not here today, but I'll tell him to change it. So for you, what is due? Last report is due, project. Last homework is due. Last practical is due. Major is due. Project presentation is due. So 5 evaluations are remaining for you. Okay, till now. So lot of things remaining, but the course content is over. Okay, thank you.